Welcome everyone, hello. So today, Aidan and I will be presenting a talk on building abstractions at the hardware-software boundary. So my name is Andrew Bitar. I'm a tech lead and manager on the compiler team at Grok. I'm joined by my colleague Aidan Wood. And today, our goal is to have you think about this question. How should we approach building abstractions in a computing era beyond CPUs? Now, this talk shares many themes with previous talks by legends in the industry that I really highly recommend you check out if you haven't already. The first one is by John Hennessy and David Patterson in 2018. They presented about how we're in a new golden age for computer architecture. So a really awesome talk. I definitely recommend you check it out. And as sort of a follow-up to that, Chris Latner then took this concept of this golden age and said, well, if we're in a new golden age of computer architecture, naturally, we're in a new golden age for compilers as well. So these are both really great talks, and I'm going to share some similar themes of this idea of being in a golden age of computing, but I'm going to look at it through the lens of abstractions. Because in computing, abstractions are ubiquitous. Now, this is a C++ conference, so I really hope this statement is not too controversial. Abstractions are how we build the complex systems of hardware and software that we see today. And we see them everywhere. You know, the way we build our applications, we have all sorts of programming constructs that we leverage to build these abstractions tailored for specific applications. We have our functions, types, inheritance, etc. And we have different programming languages that operate at different abstractions, right? We have very high-level programming languages. At the highest level, typically you see these domain-specific languages. You know, in AI, many of us are familiar now with PyTorch and TensorFlow. And we have lower-level abstractions or lower-level programming languages. And we have programming languages that span many different levels of abstraction. I believe most famously our beautiful language that we all love, C++. Or maybe we don't all love, I don't want to presume. This is a C++ conference though, but C++ really tries to borrow many different concepts from many different abstraction levels into a single language. And compilers, of course. Modern compilers, many of them are implemented as multipass compilers with this gradual lowering from higher level representations down to lower level representations, you know, a la LLVM, if you've been exposed to that. And abstractions are not unique in software, that you see them all the time in hardware as well. You know, in hardware CAD flows, you also see this gradual lowering from hardware description languages down to gates, for example. And even how we build hardware, you know, how logic designers approach building these complex systems of hardware. Often they resort into block hierarchies, for example, and they leverage abstractions heavily in that regard. Now, no matter, you know, what set of abstractions you're using or, you know, what domain you're in, if you're using any form of abstraction, it's often visualized in the following way, right? You sort of have this stack of blocks, right, where one block builds on top of the blocks beneath them. And that's how we represent and think about abstractions oftentimes when we're using them. And moving up and down that stack, oftentimes the continuum or the trade-off is at the lower level you have sort of low-level control, and as you move higher and higher up, you're trading away some of that low-level control for usability, structure, and speed of development. Now, software developers often think of mostly the top 2/3 of the stack that I'm representing here, and often forget that hardware also has various different levels of abstractions that they use to build. And in between the hardware and software is a very important abstraction layer, this hardware-software contract that I'm referring to, or that's commonly referred to as the instruction set architecture, or the ISA. Now, no matter at what level you're operating at, or no matter what abstraction you're using, it's often under the assumption of using this sort of abstraction contract that I'm referring to, where basically the agreement is, if I'm offering you an abstraction, I'm saying, here, use this abstraction, it's going to get you great usability and control, and there's a bunch of low-level details that don't worry about it, I'm going to take care of it with this abstraction, right? And promise that I'm going to take care of it better than you could. Now, unfortunately, this abstraction contract is broken all the time. We offer these abstractions, and they're often, to use a term coined by Joel Spolsky, they are leaky. Right, where no matter the abstraction's best efforts to hide these lower level details, inevitably, as I really try and get sort of maximum amounts of performance out of this abstraction, I feel the presence of those low level details. And the only way in order to get the performance I need is oftentimes peeling away that abstraction layer and using and operating at a lower level. So this concept introduces this notion of the abstraction trade-off, right? Because abstractions are rarely come for free. Now, Chandler Kurth, who I believe is doing a keynote tomorrow that I'm very excited about, he proclaimed at CppCon boldly that there are no zero-cost abstractions, absolutely none. He gave actually a really great example during that talk where he showed that even using something as simple as unique pointer comes at a runtime cost. Now, despite this cost, we often take advantage of these abstractions nevertheless. We say that cost is worth it, it's often minimal, the abstraction is very well designed, it's worth it for what the abstraction provides me. Now, this all depends on how the abstraction is designed and the application that it's used for. So there are oftentimes a set of abstractions that makes no sense for a given set of applications. And a great example in the Hennessy and Patterson paper that was related to the talk that they give, they show an example of implementing matrix multiply at different levels of abstraction. And they show the orders of magnitude difference in performance depending on how low level you're operating at. So they show at Python you're getting the worst performance, then you operate at C and you get a 47x speed up just by going from Python to C. And then as you use lower and lower level hardware constructs, you get additionally orders of magnitude levels of performance improvement. So to just generalize this concept of having this abstraction trade-off, to visualize it in sort of a more general way, I'm sort of going to illustrate this representation to speak to it, right? So for any given application, right, you have a peak level of performance that you can in theory achieve depending on what abstraction level you're operating at. And so this is what I'm demonstrating here. You have your y-axis representing the peak achievable performance for a given application, and your x-axis, which is the software abstraction level that you're operating at. And depending on the abstraction set that you're using and what application you're targeting, you're going to see some kind of relationship that is generally either going to be mostly flat or most of the time moving downwards as you operate at a higher level of abstraction. And this all depends on how you design these abstraction levels. So one thing that happens is whenever an abstraction is developed, the cost that you pay for using it is sort of accumulated up the stack in the sense that that abstraction, the cost that you pay, is not recoverable based on the abstractions that are built on top of it. So it is critical for us, especially at our lower levels of abstraction, to design very effective abstractions that minimize that cost that's paid. Because whatever cost that's paid, that cost is incurred upwards the stack. So anything that you build on top of it can never recover the cost that it paid when it decided to use the abstraction that you offered it. So as software developers, we spend a lot of time meticulously optimizing these abstractions to minimize their leakiness, to maximize your ability to get the speed of development and control while minimizing the cost that you pay for using that abstraction. However, we spend all this time doing this, but we often ignore the very left-hand side of this graph, right? The foundational abstraction level that all software stacks are built upon on top of, and that is this hardware-software contract that I was referring to earlier, the ISA. The ISA sets the limit of achievable performance for your architecture, right? Any software stack that's built on top of a given instruction set architecture is bounded by the performance that ISA offers you for this application. So while software developers spend a lot of time meticulously improving their software stacks, they often view the ISA as almost like a sunk cost, right? It's hardware, it's fixed, right? This is the price we pay for doing compute. Now, during this talk, I'd like to revisit this. I'd like to sort of explore this idea of how can we build a stronger foundational abstraction that maximizes the achievable performance of the compute on our chip. So in order to answer that question, we need to look at a little bit of history and view it through the lens of architecture as being sort of this bedrock of abstractions. And so some of this history is gone into quite a bit of detail in Hennessy and Patterson's paper and talk. So I'm going to go over it a bit briefly. Hopefully some of this is already a review for many of you, but if you'd like more detail, I encourage you to check that out. So during this first golden age of computing that Hennessy and Patterson talk about in their paper, the first sort of instruction set that was exposed to software developers was CISC, right? Complex instruction set computers. And they were born in an era where programs were primarily written manually using assembly languages. So it made sense to raise the abstraction level that these programmers operated at because they were writing them manually. So it made sense, as they designed these ISAs to sort of group multiple operations that were often done together as a single instruction. Now, of course, this changed. As we sort of moved away from manually written assembly towards using or leveraging more higher level languages, the question changed from what assembly languages would programmers use to what instructions would compilers generate. And many of us already know the story. Computer architects then began to explore RISC-style ISAs, or reduced instruction set computers, right? Where essentially what happened moving from CIS to RISC is it essentially lowered the abstraction level of the ISA exposed to software. So this had a couple advantages, right? So one is it moved some of the complex control logic that was used to sort of decode these CISC instructions and move that responsibility to software, therefore freeing silicon area for more compute and memory, right? So many experiments at the time, especially ones that are talked about in Hennessy and Patterson's paper, they show the degree to which you could get performance advantages by using RISC-style architectures. So not only did you expose more silicon area for more compute, you also gave software more low-level control. And they demonstrated that software is able to take advantage of this to make better decisions when exposed to this sort of lower-level abstraction. So computer architects at the time saw this trend, and they said, okay, can we take this even further? Can we take this trend of moving some of this complex control logic from the silicon area of the chip, move that responsibility to the software, and expose more area for more compute and memory? And so one approach that was taken sort of afterwards was this notion of VLIW. So computer architects saw that there was all sorts of control logic dedicated to caching, prefetching, out-of-order execution, branch prediction, which costed significant amounts of area on the chip. VLIW, what it did is said, okay, let's try and move some of that responsibility to software. So things like execution ordering, data prefetching, for example. It was the compiler's responsibility to achieve maximum levels of instruction level parallelism. Now, one of the most famous attempts at implementing a VLIW architecture was Intel's Itanium, that many of us are probably familiar with. And of course, as the story goes, Intel Itanium didn't succeed, and there were many reasons for this. One of the reasons was the compiler struggled to achieve the instruction level parallelism that was promised by the architecture. And one of the reasons for this was that the compiler struggled to reason about dynamic behavior of the program. So things like cache misses, dynamic memory dependencies, dynamic branches, because the compiler only had a view of behavior at compile time and no ability to predict or to have predictable view of the dynamic behavior of the program, it had a very hard time rationalizing about when these cache misses occurred and when certain memory dependencies would be dynamic and therefore make it very difficult to maximize the efficiency of the hardware. And so because of VLIW's failure at the time, CPUs proceeded to employ mostly CISC and RISC-style architectures for several decades afterwards, and it became sort of the dominant form of compute that we saw. And then in 2012, something changed. AlexNet came onto the scene as sort of this breakthrough for deep neural networks. Now, this was a bit peculiar. Observers sort of looked at this and said, okay, AlexNet employs convolutions and backprop, operations that have existed since the 1980s. Why did it take till now in order to see that these were powerful tools that we could use to better implement applications such as computer vision? Well, throughout those decades, as we talked about, CPUs were the dominant form of compute, and CPUs were poorly suited for executing these type of data flow heavy applications. CPUs paid significant amount of area for control flow logic that these data flow type of applications didn't need, right? And so they were poorly suited for these type of applications that focused heavily on data flow style compute. And so it was sort of accidental with the evolution of GPUs, were originally for graphics processing, of course, but also offered an architecture that had more data flow heavy computations, that it reduced the amount of silicon area dedicated to control flow and more towards data flow style compute like fixed and floating point arithmetic, for example, that these deep neural network style applications heavily used. So this notion of what architecture or what hardware is available at a time limiting the type of algorithms that we explored is referred to by Sarah Hooker in a really great paper as the hardware lottery. And she actually came to Grok, one of our Grok Day events, and gave an excellent talk that I encourage you to check out. So this concept of keeping in mind that the way we develop algorithms can often be limited by the architectures and the hardware that we have available at any given time may limit our ability to implement the optimal solutions for the type of problems that we're facing. So with the advent of GPUs and with sort of the explosion of these data flow type of compute, GPUs began to flourish. They sort of evolved into not just GPUs, but general purpose GPUs. So rather than just being domain specific in graphics processing, they started taking on wider and wider sets of applications. So this notion of limiting the amount of silicon area for control flow and maximizing the amount of data flow on your silicon is a method that we sort of just covered, right? It's a similar approach that what VLIW attempted to explore. So the question is, what's changed? Well, again, it's this idea of a new way or a new type of applications and algorithms for implementing or tackling some of the problems that were traditionally implemented using rules-based approaches. So this emergence of software 2.0, where essentially employing these data flow style algorithms that computer scientists demonstrated would achieve even better performance than the classical methods that we had been employing. And so this has brought on sort of this new golden age of computing with the end of the CPU hegemony. Now, not the end of CPUs, but the end of CPUs as the only computer hardware that we can build our solutions, our algorithms for, right? With this growing demand in data flow dominated compute, as well as the slowing of Moore's law and Dennard scaling, the CPU abstraction is no longer the only foundation for developing software. So this new golden age of computing, it comes in many forms. It's not only a new golden age of computer architecture or a new golden age of compilers, but it's also a new golden age of algorithms, right? How we approach building solutions for the problems that we're facing today is not solely just these rules-based programs, right? We can explore new types of methods like data flow, deep learning, right? So whereas in the past, we had sort of this fixed hardware, the CPU, that we sort of had to deal with and figure out how to best build our software, so we had hardware defining our software, now the hardware-software abstraction contract has been reopened. And we can explore maybe inversing this relationship, right? Rather than having hardware-defined software, perhaps we can now explore achieving software-defined hardware. And at Groq, that's exactly what we sought out to do with our chip. At Groq, with our architecture, we are trying to radically simplify compute. And I love this photo. This is a photo of our die, and it really illustrates, I think, the simplicity of the architecture, specifically provided by the fact that we've minimized as much as possible silicon area dedicated to hardware control in order to open up more area for compute and memory that are really necessary for these data flow style algorithms. So the details of our architecture are gone into a lot of detail in our two ISCA papers that I very much encourage you to check out. We go into all sorts of details about how the architecture works. We have one in the year 2020 and our most recent one in 2022 that I highly recommend you check out. It'll go into much more detail than I'll have time to get into today. So this is an overview slide sort of talking about the high-level features that the architecture is offering, all the high amounts of memory bandwidth, compute bandwidth, networking bandwidth that the chip has to offer. But in order to really get into understanding why this architecture overcomes some of the hurdles that previous attempts at creating data flow architectures faced, we really need to get into the details of the fundamentals of the architecture. So in order to explore this, I want to get into the building blocks. So the fundamental building block of the Groq chip is this SIMD unit. We also refer to this as a functional unit. And these SIMD units are able to execute a set of vector operations where our vector size for the first generation of our chip is 320 elements. So for each of these functional units, they have the execution units, and then it has a dedicated instruction dispatch logic. And that instruction dispatch is very lightweight, and it issues an instruction every clock cycle to the functional unit. So you could think of this almost as a base class of the architecture. And so what we do is we take this base class and we specialize it, as you might do in software. We create types, right? With each type dedicated to a specific set of operations. So we have our MXM unit on the very left-hand side of the slide, or the right-hand for the audience, that is dedicated for matrix vector and matrix multiply and adds. And so this is really fundamental to many data flow style algorithms. It can implement very efficient matrix multiplies or matrix vector multiplies. We have our vector unit, the VXM, that's capable of doing vector operations. Now, of course, if you look at any sort of end-to-end data flow algorithm or deep learning algorithm, it also employs a bunch of data reshape operations. So we have dedicated units for that, or SXM. And then, of course, we need memory on chip. So we have high bandwidth memory units as another specialized functional unit on the chip. So in order to fill the silicon area of the chip, to fill the space that we have, we take our types and we lay out multiple copies of the types horizontally across the chip. So we have many different MXM, SXM, MEM units, VXMs, and these are not the only types on the chip, but I'm just showing them as the key examples of what we have available. And so let's bring back the instruction dispatch that we were referring to earlier. So we have each of these units having their own dedicated instruction dispatch, and we want them to be able to operate in a way that is that a compiler could potentially target. And so we have the instruction dispatch units executing in lockstep. They have this common time domain. So they share a clock cycle, and they each are issuing an instruction at every single clock cycle to each of the functional units in lockstep execution. And finally, we want these functional units to be able to communicate with one another. So we introduce these data flow paths that we refer to as stream registers. So we have these two high bandwidth stream register paths flowing eastward and westward along the chip that allow the functional units to communicate. So this illustrates the foundational structure of the architecture. So now we have to explore, okay, now that we have this image of the architecture, how does this actually allow us to build a compiler for the chip? So to answer this question, we have to first look at other spatial architectures and what challenges they face in building a parallelizing compiler. So other attempts at creating spatial architectures have faced various challenges in attempting to do so. And I want to enumerate them clearly here to address directly how we're addressing these challenges. So one common challenge that's faced in these spatial architectures is this notion of unpredictable memory latency. So many of these spatial architectures either rely on caching mechanisms or heavy reliance on DRAM, these dynamic hardware components essentially that make it very difficult or impossible for a compiler to reason at compile time about your memory access latencies. And so without the visibility of this at compile time, the compiler will struggle to understand how long this access will take, and therefore how can I actually hide that latency by maximizing the efficiency of the compute units on the chip during those accesses. And architectures often have to rely on adding dynamic hardware to the silicon area in order to ensure that that latency can be hidden, right? And that control logic will either take away silicon area, or if you don't dedicate silicon area for doing that, then you move that responsibility to the compiler, and the compiler struggles to do this because it doesn't have that visibility. The second challenge is thread synchronization. So oftentimes these spatial architectures are made up of multiple different cores that are all implementing dedicated compute. And oftentimes the reliances have said, okay, we're going to divvy up our program into sets of threads, and each of these threads have sets of instructions that we're going to allocate to these different cores. Now, oftentimes these architectures have a mechanism where these threads are sort of allocated to these cores asynchronously, where they don't share a common domain. Sorry, let me get rid of. Sorry about that. So they don't share a common time domain, right? So these threads may finish at different times. And this makes it very challenging, of course, for the compiler to rationalize about resource allocation, for example. If thread X and thread Y are operating asynchronously, the relative times at which they finish at compile time are unknown. And so the compiler will have a hard time understanding when a resource becomes available in order to allocate another thread to that core, for example. And so again, you're left with the option of having dedicated hardware control that does this thing dynamically and eats up silicon area, or you have the responsibility on a compiler, and again, the compiler doesn't have that visibility at compile time. And finally, the third challenge I'm enumerating here is the complexity of the interconnect. So again, oftentimes you have these multiple cores and they need to speak with one another as well as with memory. And so architects often employ these systems of interconnects that have a bunch of fancy dynamic hardware to allow very efficient passing of data between to optimally share these wires that are precious resources on the chip. And so they'll have things like arbiters, queues. If you're worried about deadlock, you'll have virtual channels. And now these are dynamic hardware components. So again, there's this challenge on the compiler to rationalize about data movement at compile time without doing sort of a full-blown cycle-accurate simulation, for example. Depending on the complexity of your interconnect, it's very hard for the compiler to know when I send data from core A, when will it arrive at core B without doing sort of a full simulation of the network. So these are often referred to as networks on chip. They're used in a bunch of spatial architectures, especially in multi-core processors. So all these challenges faced by a compiler for spatial architectures often leads to companies or architects of almost abandoning this notion of implementing a true parallelizing compiler. So companies like NVIDIA, for example, or others will take the resort of building libraries of hand-tuned operations, or kernels, if you will, right? These kernel libraries, if you've ever developed using NVIDIA's cuDNN stack, for example. And these libraries are hand-tuned by people. They will go through the process of profiling the operation and understanding how to maximize the efficiency of the hardware by hand. Now, this approach can work, but it scales very poorly, and it requires intensive engineering hours that are very expensive. And anytime the architecture changes with your new generation of the hardware, or if the sets of operations that you care about change, suddenly your team has to get back to the drawing board and re-implement a bunch of kernels, right? This approach can work for a company like NVIDIA that's massive and has massive teams available. But to get to that point for any other company is a challenge, right? So it's very key that we think about an approach that's scalable. How are we going to scalably build software for our spatial architectures? And at Groq, that's exactly what we sought out to do. We sought out to build an architecture abstraction that specifically addresses these challenges in order to empower the compiler to maximize the efficiency of the compute available on the chip. And these are the 4 features I'm going to get into that sort of illustrate why the compiler has this capability. So the first is software-controlled memory. Absolutely no hardware caching. The software has full control over the memory in the chip. The second is a very simple interconnect. Third, we have specialized location-specific functional units that execute entirely in lockstep. So now let's get into the details of each of these to really comprehend why the compiler can sort of take advantage of these to maximize the efficiency of the compute on the chip. So let's first talk about memory. So I mentioned software-controlled memory, no dynamic hardware caching. The compiler is aware of all data locations within memory at every cycle of the program. So there's no hierarchies of caching, there's no L1, L2, L3. The compiler can directly address the physical banks on the chip, and therefore has an exact view of where data lies in memory at every single cycle. Now, another sort of key component of this architecture is the very large memory capacity that we have on chip, as well as the high amounts of bandwidth that we have available. So we have 220 megabytes operating at very high 80 terabytes per second of concurrency. Now, of course, you're going to have programs that don't necessarily fit entirely on chip, especially with the size of the deep learning models that we're seeing today. But the key is that with this high amounts of on-chip memory capacity, as well as the bandwidth, it allows the compiler to hide the accesses to DRAM that are inevitably non-deterministic. So because we have this amount of memory capacity and concurrency, we can keep our compute units fed for long periods of time as we do these DRAM accesses. Now, secondly, in order to be able to take advantage of the compute and give the compiler, the power to schedule on the hardware, the compiler needs to have full view of instruction timing throughout the execution of a program. And so this is enabled by the fact that the functional units are executing in lockstep with fully pipelined execution. So we have each of our functional units issuing an instruction every single cycle. So this can almost be viewed as sort of a fully pipelined 144 wide VLIW. Architecture, right? Where you have 144 instructions issued to all the functional units at every given time. And so this allows the compiler to understand every cycle what instructions are executing throughout the chip. Now, the added bonus of implementing this scheme is it actually is very cheap in hardware, right? It's taking up very little silicon area to do the instruction dispatching logic. So less than 3% of our silicon area is dedicated to instruction dispatch. Now, the compiler doesn't only need to understand instructions scheduling over time or issued over time, it needs to have understanding of it executing over space of the chip as well. So the ISA explicitly exposes the types of functional units that are available on the chip and their specific locations relative to each other throughout the chip's area. And so with this information, the compiler can understand exactly where each instruction can be executed throughout the chip's physical space or area, right? And so this gives the compiler a lot of capabilities. So this, combined with the previous slide, gives it the ability to, view all instructions executing over time and space, but it also gives it very interesting capabilities to make decisions of how to map a program with its different shapes and sizes throughout the execution to the available hardware. So I mentioned that we have multiple copies of each given functional unit type. The compiler is able to use those multiple copies for more concurrency in a sort of a SIMD-like fashion, or it can use it for more pipelining in a some more MIMD-like, where you're sort of pipelining the data through with each stage executing a different instruction. And finally, I talked about the importance of interconnect. The interconnect on the hardware is explicitly very, very simple. It's a one-dimensional interconnect with 2 paths, essentially, for interfunctional unit communication, an eastward path and a westward path, with each path being employed by an array of stream registers, where a stream register, you could view it as essentially a one-hop or one-cycle hop along the path, right? So there are absolutely no arbiters, no queues, there are no dynamic hardware components, which allows a compiler to very easily reason about the exact data movement throughout the execution of a program without the need of simulation. So travel time, for example, is as simple as a single subtract or add operation of figuring out where your functional units are relative to one another and the number of hops in between them. Now, oftentimes, I would say nowadays, especially in this world of HPC and high bandwidth deep learning applications, one chip is not enough. You often need a network of chips. And so at Groq, we take this very seriously. And we've extended this notion of lockstep execution to a network of Groq chips rather than a single one. We'll have time for questions. Please hold it, yeah. So we have the ability for the compiler to schedule a system, a full network of Groq chips from a single node to multiple racks. It can schedule the system of Groq chips as one. It has full view of deterministic execution throughout the system of Groq chips. And this is very powerful, and the details of which we get into in quite a bit of detail in our recent ISCA paper. So I encourage you to check that out if you want more information. So putting this all together, the compiler has full power of data orchestration. It can view at every single cycle of the program where data lives, where it's being executed, and where it's being sent. That's pretty cool. This is a video of our Grok view tool, and it takes a compiled program, and it's just visualizing all the information that the compiler has available to it. It's visualizing essentially the fact that the compiler has the information of all data movement across every cycle. So you could freeze this animation at one point, and it will represent, for example, cycle 2000. And at cycle 2000, you'll be able to see the compiler knows I have data here, here, here. It's being executed at this functional unit. It's been stored at this memory. Every single cycle is deterministically known at compile time. That's immensely powerful. So we've talked about this sort of at an abstract level, if you will. So let's get a little bit more concrete as to what this enables a compiler to do. So I'm going to pass it over to my colleague Aidan, and he's going to work through a simple but concrete example to illustrate what type of power we have with this deterministic architecture.
All right. Hi, everybody. My name is Aidan Wood. I'm an IC at Grok. I'm on Andrew Bitar's team. And so, yeah, I'm going to walk us through a quick example on a theoretical SIMD architecture with caching and multiple cores versus how this is going to occur on the Grok chip. So our compute is really simple. We have 4 vectors. We want to sum them together into a single result vector. So if we want to execute this on one thread, it's pretty easy. We just assign everything onto thread 0. You can see that the compute is structured in a way that we can parallelize in the middle there. We fan out to the left and the right, where we can theoretically do that at the same time. So let's do that. Let's have, when we fan out, let's assign half of it onto another thread, thread 1. And then we're going to come back together on a thread 0, and then return. So if we compile this on some theoretical SIMD architecture with cache, we're going to see something like this. This is probably what, as C++ programmers, we'd imagine to see. So we have 2 functions. Function add2, very simply. It loads 2 operand vectors, it adds them together, and it returns. Add4, which is kind of our whole program, it's a little bit more complicated because we have to deal with this synchronization problem between the threads. So first of all, we're going to dispatch onto thread 1, which is going to do our one half of our intermediate adds. And then we're going to execute our own instance of add2. And then we're going to join thread 1. Once we have that intermediate result, we're going to execute our final add, and then we're going to return. So here we have a quick diagram. So you can see that on this theoretical multi-threaded SIMD processor with cache, we have L1, we have 2 cores. They're connected by main memory. So executing this program, starting at time 0, we're going to start executing add4 on core 0. Immediately, we're going to send an interprocessor interrupt, also known as an IPI, over to core 1. This is dispatching our second thread. So this is going to send this over. It's going to say, hey, core 1, start executing an instance of add2. So immediately, then on core 1 is going to continue, and core 0 is going to continue and execute its own instance of add2, whereas on core 1, it's then going to first have to initiate a load from main memory. So hopefully at some point, we're then going to have a situation like this, where we see what we want. We have the compute occurring in parallel on core 0 and on core 1. So then we're going to see on core 0, it's going to finish its compute first. And it's going to begin joining onto thread 1. So thread 1 is going to continue its execution. Eventually, it's going to end. So see, we're at a time here, tdispatch plus tadd. This is the time that it took for the IPI to occur, and then the time that it took for the add to finish on core 1. So then, we're still joining on core 0. On core 1, we're going to initiate 2 stores. We're going to have a store of I1, which is that intermediate result it computed, and also it's going to store its thread state, saying to main memory, hey, I'm done. So immediately, you're going to see a cache miss. On core 0, it was pulling on that thread state on main memory. So it's then going to load the thread state. It will then see that, hey, this thread is done. Okay, that's great. I can proceed. Immediately going to cache miss again on that intermediate result that was computed by core 1. Going to initiate another load. But now, great. Now you have both that I0 and I1. That was I0 computed on core 0. I1 computed on core 1. It's going to add those together and return. It's great. So looking at this overall latency, you can see that we have a total of 6 terms, and 5 of them are not resolvable at compile time. So tdispatch, it's implemented via interrupt, and it's a consequence of having this more complex arbitration system between the cores. And then our 4 other elements are due to, we just don't know how long it's going to take to do these memory accesses. We have a complex memory hierarchy here. This is a cost that is incurred because the ISA only exposes the idea of a load. You don't really know where that load's going to end up accessing from. So now we're going to look at how this would occur on the Groq chip. So this is that same computation graph, and we're going to do an allocation of what functional units will be used on the Groq chip. It's going to look something like this. So we're going to have up at the top, we're going to have our memory units are going to initiate the reads of all of our input vectors. And then we're going to have VXM0 and VXM1 are going to complete the intermediate additions. We're then going to have those intermediate results sent over to another VXM unit, VXM2, where it will then send its result back to memory to be stored. So if we look at the compiled contents, this is how it will be stated imperatively. So you can see on line 1, we have our memory reads. Line 2 and 3, we have our intermediate adds being completed. Line 4, our final add, and then a store. However, this is what it actually is going to end up looking like. So you can see that there's no imperative structure to this code. It's actually in a much more flat structure. You can see that every single hardware, it's the functional unit, has a number of instructions, and they all have a specified time step. You gotta remember, this is because we don't need to do synchronization. We have this idea of all these hardware units progressing in lockstep. So all they need is a time and an instruction. And it's up to the compiler to coordinate that data is moved around the chip in such a way that these instructions actually do the right thing functionally. So now we're going to look at this with an example. So here we have a diagram. This is a small slice of the Groq chip. So we have, on the left side, we have 4 memory units, and on the right side, we have 3 VXM units. They're connected by the streaming register file. You can think of this as kind of like a highway, where it can go left and it can go right. So it sends data between these functional units, and in each direction, you have a number of lanes. Each lane carries a full vector of data. So it's going to happen at time 0. We're going to initiate all of these reads from memory. So after these reads are finished, they're going to push data down to the streaming register file, where it's then going to hop on this highway. But we know how this highway works. It's that every single cycle, it goes kind of one stop further. So you're going to see it kind of progress over to the right towards the VXM, where eventually, after time t travel, it's going to arrive at VXM units 0 and 1, where we're going to push in these input vectors. They're then going to be added together, computing these intermediate results. And then we're going to see after they're done, they're going to push their intermediate results down back to the streaming register file, where they're going to go one more hop to the right, going to end up at VXM2, where then we're going to add these intermediates results again. Once it's done adding, push back down to the streaming register file, this time moving over to the left in that same fashion, one more cycle, one more hop, getting closer and closer, finally ending up at main memory, where it's going to be stored. So after the store is done, we're done our program. This is great. So now we're going to compare our latencies. So you can see on the Grok chip, we have 4 terms, and all of them are completely resolvable. This is super important. We know how long our memory accesses are going to take. We know how long it's going to take for the data to travel between these units. And we know how long it's going to take to actually do the computation. And this enables the compiler to parallelize without the need to synchronize. And that's key. If you look at this, this is in stark contrast to our theoretical SIMD processor, where although we have maybe a bound, if you know the hardware system you're targeting, on how long it's going to take to perform this computation, on a run-by-run basis, you just don't know how long it's going to take. And for real-time systems, this could be incredibly punishing. And this is the cost that comes with this kind of parallelization. So, what we know is that this unpredictable hardware, it can cause pain for users. That pain can come in 2 main forms. If anyone's ever written parallel code for CPUs, it's really hard. Writing parallel code is extremely difficult. You have to deal with lock contention, you have to deal with deadlocks, you have to deal with every problem you can imagine under the sun. So many problems in multi-thread code just come down to race conditions that you don't foresee when you're designing these systems. Or it can be pain in terms of latency. If you think on your 99th percentile of a program execution, you get a bunch of cache misses and suddenly it's taking some time amount longer. It could be massive, and this can be incredibly punishing. Think about like game programming. You get a lot of cache misses, your performance tanks. So, but you have to remember, this is actually not a sunk cost. This is this idea of parallel code being complex and being difficult. This is actually a problem with the architecture. This is because the architecture only exposes these things like memory locality, but only at a flat level. You just initiate a load. You don't know where it's actually coming from. And when you say you want to do compute, you don't really know how long that might end up taking. So, predictable chips offer an alternative, like the Grok chip. When you initiate a compile, you get a statically scheduled program. It gives you an idea of exactly how long these operations are going to take. Everything operates in lockstep. You know at a cycle level how long your computation is going to take. And this gives this control given to the compiler through these systems, gives you the ability to do highly performant compute parallelism in a completely automated way. This demonstrates on how focusing on changing the abstraction levels that the ISA exposes to software changes the way that we program. And that when we're as programmers, it's part of our job to think about what these abstractions are presented to our software because it changes the solutions that we think about when we're trying to solve engineering problems. I'm just going to pass it back to Andrew here.
All right. Yeah, so hopefully that example sort of gives some concreteness to what this type of architecture gives in terms of power to the compiler. It sort of illustrates the real transparency of the architecture. Now, beyond sort of the empowering of the compiler, this architecture actually enables to do some very interesting hardware-software co-design using the compiler that we've built. So I'd like to get into that a little bit here to show sort of another cool feature that we have. So this is a high-level view of the Grok compiler flow. So we take, for example, in the deep learning space, we take your standard frameworks as input, for example, your TensorFlows, your PyTorch, and we do a gradual lowering of these higher-level representations down to lower-level representations. In this case, we have individual vectors that are scheduled by the compiler on a cycle-by-cycle basis throughout the execution of the program. Now, one very great effect of sort of this deterministic architecture is not only that the compiler has full view on a cycle-by-cycle basis, but that the compiler can then, at compile time, let you know the exact performance of your program down to the clock cycle. So I don't have to ever need to run the code on the chip in order to know exactly how long it's going to take down to the clock cycle. That's pretty cool. And it gives us really powerful capabilities that we can leverage using our compiler on its own. Now, in order to be able to do this, we need to have a model of the chip represented in the compiler. So we have this Grok chip model, which represents a software abstraction of the architecture, giving the compiler all the information that it needs to do this detailed level scheduling. So let's get into this a little bit. So the architecture is actually providing a very natural fit for this type of software abstraction of the architecture. So how do we represent all this different information? So recall when I was describing the architecture, we had this base class functional unit, and then we specialize it. Well, this fits very nicely with C++'s concept of templated polymorphism. So we take our functional units and we represent them in this way. Now, each of these functional units have their own instruction sets, and each of these instructions have their own latencies, so we encode that information in these lookup tables, again represented within software. We also need to be able to rationalize about data movement. So we talked about this simple one-dimensional interconnect, and we can abstract that also by representing each functional unit as living in a given time zone index. And so we talked about how travel time between functional units is quite trivial with this interconnect. It's as simple as calculating the difference between two time zones. So that's a very efficient lookup. And finally, we need to be able to do resource allocation on a cycle-accurate basis, and we employ dedicated data structures to do this. So one method we employ is leveraging bit vectors, for example, for doing range-based allocation and lookup across time and space, which is a necessary step for compilation in this process. So all these ingredients together, plus more that I'm not going to get into in this talk, gives us an abstraction model of the Groq chip and allows us to do cycle-accurate scheduling for any chip that can be represented within this model. So this whole flow gives us a very powerful ability to do dedicated hardware-software co-design, a methodology that modern architects say is key in this sort of new golden age of computing, where we can sort of, for example, take a benchmark set that we particularly care about and use this chip model abstraction along with a compiler to assess different permutations of the architecture in order to determine what's the optimal architecture for this benchmark set. And this is all enabled by this very fast and efficient abstraction model of the chip, as well as the deterministic nature of the architecture that allows the compiler to not only tell you the exact number of cycles it's going to take for your program, but also determine utilization of your different functional units. For example, are you bottlenecked on a specific functional unit type? Is one functional unit underutilized? Take that information and feed it back into your exploration tools. And you could do the inverse type of code design as well, where you have a set of architectures that are exploring, and you also want to tune your benchmarks or design your algorithms to better be tailored for the architecture. So this hardware-software co-design mechanism is all enabled by the compiler. We don't need to build a chip in order to explore the different types of different parameters of the architecture that might be best suitable for a given domain. Now, this notion of using software and the compiler to do architecture exploration or hardware-software co-design is not new to our chip, and it's not unique to our chip, certainly. This has existed in many other architectures, and one really great analog I want to bring up is FPGAs. FPGA CAD flows have provided an ability to do this type of hardware-software co-design for decades, right? So for those who don't know, FPGA CAD tools take your hardware description languages and progressively lowers them all the way down to a bit stream that configures your FPGA's lookup tables that will be emulating gates in your circuit, as well as the routing fabric as different switch blocks to connect these gates together, plus hardened blocks that are dedicated for specific functionalities like memory or DSPs. So the FPGA CAD tool, it compiles your hardware description language, but it's also able to provide you the metrics you care about at compile time, similarly to our flow, right? Things like resource utilization and Fmax are what hardware developers care about, and the compiler gives you this at compile time without necessarily needing to load it on an FPGA or have an FPGA device available. So in order to do this, the compiler requires a detailed low-level chip model, right? It needs to be able to represent all the architecture information in software. And so one of the best examples I like to refer to as an open source FPGA CAD flow that's been around for a long time now, Verilog to routing, VTR, developed at the University of Toronto actually. And VTR has been long used by FPGA architecture researchers as a tool to explore different FPGA architecture permutations to better optimize their architectures for the sets of HDL or programs that they compile. So this was actually originally introduced 2 decades ago, in the year 2000, by my former supervisor, Dr. Von Betz, and his supervisor, Jonathan Rose. So this is just a visual description of VTR. So you see on the right-hand side sort of this progressive lowering of your hardware description language down to a net list, down to a place and route net list, all the way down to a bit stream, and then coming out on the output, that's a bit small, but it gives you all the metrics that you care about along with the bit stream that gets programmed. And feeding into that flow is this abstraction model of the architecture, where it represents all the different parameters of the architecture that you may want to explore, things like mixtures of resources or types of routing fabric that you want to explore. So hopefully you can see sort of the analogies between this flow and the flow that we have at Groq. They're representing sort of different domains. One is for hardware programming, and another is for data flow compute. But the ability to do this hardware-software co-design is in both cases enabled by the compile flow that's presented by the architecture. So let's wrap up. We've gone on quite a bit, and I'm getting the cue that there's only a few minutes left. So hopefully by now you've been convinced maybe that we're in a new golden age of computing. And if you need any other evidence, is the sheer number of acronyms we have now for different types of architectures. We have TSPs, TPUs, RISC-V, FPGAs, CGRAs. That's not even half, I would say. This is maybe 10% of all the different architectures that we have and the acronyms we have to describe them. And what this really represents is that the contract between software and hardware has been reopened for negotiation. What responsibilities should we have in our hardware versus our software can now be re-explored. Now, in order to make this assessment, abstractions are key. Thinking about, if we expose certain low-level control of software, can software effectively take advantage of it? And if low-level control is hidden from software, what performance may be lost in this process? And as well, what type of hardware cost may we pay if the hardware is dedicated for that control flow? And finally, no matter what abstraction we design, is that abstraction leaky? Are we able to give the necessary control and hide the necessary details without having that pain points, that those low-level details leak through the abstraction that's presented by the ISA? So designing such a good abstraction requires thinking carefully about the target applications. We talked about, data flow and control flow, and the applications that we see in algorithms that will be developed will inevitably have a mix of these two things, right? And we'll have potentially large amounts of data flow for certain types of applications or large amounts of control flow for data for certain applications. And considering these mixes is key when designing these types of abstraction. So to put it all together, hardware-software co-design is key. Right? I'm not the first person to proclaim this. Any computer architect that you talk to nowadays will say, now with sort of these new type of architectures, we need to explore these two things in tandem, right? This whole idea of exploring hardware, compilers, and algorithms all together in a full co-design flow to develop a better end-to-end solution that meets the challenging problems that we face today. Thank you very much. At Grok, we are also hiring, so if you're interested, feel free to contact us. And I think we have some time for questions, hopefully, so we'll take them now. Thank you very much.
Beautiful architecture. Looks like it solves a lot of problems. I think maybe for this audience, there's kind of a little bit of context that may have been left out because the first thing I was thinking is, well, what happens to all of that predictability as soon as you have a conditional branch? Of course, you can't have conditional branches in this system, right? If I'm not mistaken.
Finish your question and I'll get to it. Yeah.
I mean, you could sort of, to some degree, simulate them, but I think this is like specifically, which you said once, for data flow computing. And I was wondering what is the programming model for this? So I assume that it's a functional data flow type programming model that you have to use, yes?
Sure, so anything else?
Yeah.
Maybe I'll answer that and then I'll let you do a follow-up.
Okay, that's great.
Sure. So you talked first about conditional branches.
Yeah.
So the architecture does support conditional branches, and that's something I didn't get into here today, but it does support them. Now the key is to what efficiency do you support these different conditional branches, right? That's the key. So when you have an end-to-end application, it's inevitably not going to be necessarily entirely data flow, right? You're going to have maybe bits of control flow throughout, right, depending on the nature of your workload. And so it's key to not necessarily always have to fall back to a CPU every time you need to do these type of dynamic operations. And so the architecture does support this. It's a matter of what the architecture prioritizes. So we prioritize doing data flow extremely efficiently, but we will support dynamic execution, and we can support it, and in some instances actually quite efficiently, but it's not the primary goal. So similarly to a CPU can do data flow compute, but it has tons of silicon area dedicated control flow because that's, if you look at the architecture, it's priority. If you look at a picture of the architecture, the amount of silicon area for compute is not even 50%, right? It's less than 50%. So it's about what we prioritize. And so we are able to support it. And in terms of the programming model, I think you were asking a question about. So the programming model is a very interesting question, and it's actually one that we're actively exploring at Groq. So currently, as part of our SDK, we offer many different ways to interact with the chip. So one, in terms of usability, is representing your workloads in the typical frameworks that data scientists employ, right? They don't necessarily care about the low-level details of the architecture. They have their model and TensorFlow and PyTorch, and we're able to take that directly and compile it, right? And we support sort of all the types of operations that they care about automatically, without needing a kernel library, I should add. We also have a very low-level API that gives you direct-to-hardware programming ability as well, so it allows you to do some really interesting experimentation and control the hardware at a very low level. There is an in-between, and those details we're sort of developing internally, so I can't speak to too much. But you can imagine sort of the fascinating types of paths we may explore in that approach for such a data flow dominated architecture. And I'll add one more point, actually. GPUs are also a data flow type of compute. And you should look at the type of programming models that they've exposed to their users, right? Largely leveraging sort of this CUDA flow where the user has to explicitly define where the parallelism exists in the code, and also try to minimize the amount of control flow that's in the code. Because GPUs, although they have control flow ability, again, it's not their priority, right? So similar type of thinking there.
The only other thing I wanted to say is that hardware-software co-design is obviously, a great answer for those hugely high-profit situations that AI is currently getting applied to. But, a lot of us need to invent new things with software and can't, build new chips, right? So there's figuring out how to actually make architectures like this useful for general purpose compute, I think would be a really interesting thing to investigate.
Absolutely. It's an excellent point. It's expensive to tape out a chip. Not everyone can do it. And so having this programmability in the architecture is necessary fundamentally. And so what we have attempted to do within our architecture is not say we're specifically a deep learning accelerator, right? We are a data flow compute accelerator. So any type of data flow application, we will be able to run very efficiently. And as I mentioned, that application end-to-end doesn't have to necessarily be entirely data flow. So this is sort of related to the previous answer. We're able to support this type of dynamic control flow on the chip. It's not our primary emphasis, right? We want to make sure we're doing data flow very well. So if your application is some pointer chasing algorithm, right? Use a CPU. CPUs are great for that. They've been architected extremely well, and they have decades of research behind it, right? For those type of control flow dominated application.
So what happens on your chip if I throw an application like that at it? I mean, is it just huge?
It's not, so it will be able to run, but you won't get the best efficiency out of the compute that's available to you effectively.
Sure, I might be wasting some efficiency, but will a CPU be running any faster?
So I don't have the data for you directly, and I also don't want to speak necessarily to something that probably the company wants to make sure we assess, depending on what hardware you're comparing to, right? Like there are different CPUs as well that are architected in different ways, and if you go beyond to RISC-V, for example, you can build like all sorts of exotic CPUs now that remove some things from the architecture and add certain things. So I can't just say like CPU compared to our hardware, because CPUs are so many different types, and some will dedicate less to control flow and more to data flow. And we may beat those type of architectures in these type of control flow, depending on what they use in their architecture. So the answer is it's a bit nuanced, but definitely it's not our primary goal. Our primary goal is absolutely data flow style compute.
So based on the previous questions, I'm wondering that it is possible that to build a general purpose CPU that is running Linux on top of Groq chips.
So let me clarify the question. You're saying build a general purpose CPU based on the Groq architecture?
CPU is like, Core i7 is a CPU, right?
Sure.
So I'm saying that instead of building a laptop using Core i7, can I build a laptop using Groq chips? and running Linux on it.
So the Grok chip is Turing complete, meaning it can, in theory, run any type of program, right? So theoretically, yes, I wouldn't necessarily recommend it. Like I said, CPUs have decades and decades of research behind them, optimized specifically for things like running Linux on your CPU, right? So I think the amount of research and talent that went behind it has produced an excellent architecture for those type of applications. So it would be a cool science experiment to try, but certainly just the sheer amount of detail and effort that went into the research behind CPU architectures makes it much more suitable for those types of applications.
Okay, thanks.
Yeah.
Is it possible to see some code examples of Groq language? And could you please clarify if it's possible to run that computation example on different architecture, like regular CPU or GPU and so on, because it was not clear.
Sure. Yes, so we actually have a booth set up that you can come by and actually see real code examples, so I encourage you to come by and check it out. So the answer is, for example, if you have your programs represented in TensorFlow or PyTorch or your standard frameworks, you can take that and compile it to our architecture, you can compile it to CPU, you can compile it to GPU, and it would be the same exact code that you run, right? So in terms of those domain-specific languages, absolutely, they have sort of many different target backends, with ours being one of them. We also have our other interface that we export as part of our SDK is Grok Api, which is a low-level API for programming the architecture, and that's specific to our architecture. So you can almost view it as like close to assembly-level programming of the architecture, if that's something that's desirable. But that's, again, because you're directly targeting our instruction set architecture, you can't just take that program and run it on a CPU. It would be a different program in that sense. So those are the two inputs that we provide today. In the future, if we have sort of in between, then it would be interesting to explore having multiple different backends for that as well. Oh, yes. We also have a paper that we just published at the ASAP conference that runs BERT base on the chip and achieves state-of-the-art performance. So we actually, I believe, have an example at our booth that we can demonstrate that. So it demonstrated two great things. So one, state-of-the-art latency. So we achieved best in the industry latency on BERT base on one device. And on top of that, we showed the deterministic nature of the architecture in terms of comparing a 99th percentile latency to our 1 percentile latency, how narrow the band is compared to any other type of architecture like GPUs and CPUs. So it really sort of shows the two benefits of the architecture, not only giving very high performance compute, but also very predictable compute.